Every detail in this story comes from real scientific research and observation. There is a galaxy in the sky tonight that you can see with your bare eyes. No telescope, no equipment, just darkness and patience in the right direction. It is a smudge, a soft, pale blur just above the star Merak in the constellation Andromeda. It does not look like much. It does not look like what it is. It does not look like something that has already decided to come here. It is 2.537 million light years away. That means the light entering your eye right now left that galaxy when our ancestors were not yet human, when the first stone tools had not yet been made, when the Earth looked out across a universe and had no one to look back. That light has been traveling toward this planet for 2.5 million years, and when it finally arrives, it lands on a hillside where you are lying on your back, looking up, understanding almost none of what you are seeing. Here is what you are not seeing. You are not seeing the trillion stars packed into that smudge. You are not seeing the dark matter halo that extends far beyond what light can show, a halo twice the diameter of anything visible, made of something that does not emit or reflect or absorb light at all, something we can only measure by the way it bends what we can see. You are not seeing the spiral arms, the dust lanes, the stellar nurseries where stars are forming right now in that galaxy while you breathe. You are also not seeing this. It is coming toward you. Not slowly, 110 kilometers per second. That is 396,000 kilometers per hour. That is faster than anything built by human hands, and it has been moving at that speed for a very long time. And it will continue at that speed for longer than the Earth has existed, and at the end of that journey, it will arrive here. The collision is not a metaphor. It is not a theoretical possibility. It is a confirmed trajectory, measured by the Hubble Space Telescope, verified by multiple independent research teams, published in peer-reviewed journals, and it will happen. In approximately 4.5 billion years, the Andromeda Galaxy and the Milky Way will collide, and almost nothing will crash into anything else. That is the part that should keep you awake. That is the part that bends the mind. Two galaxies, each containing hundreds of billions of stars, will move through each other, will reshape each other, will tear each other into something unrecognizable, and the stars themselves will pass without touching. The distances are too vast, space is too empty. What looks from the outside like a catastrophic collision is, on the inside, almost silence. Tonight, you are going to cross that distance. Tonight, the 4.5 billion years between now and then will compress into something you can feel. You are going to watch the sky change. You are going to stand inside the collision. And at the end, you will understand something about emptiness that is very hard to understand any other way. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. There is a number that is worth sitting with before anything else. 2.537 million light years. That is the current distance between the Milky Way and the Andromeda Galaxy. A light year is the distance light travels in 1 year, moving at 299,792 kilometers per second, the fastest anything in the known universe can travel. 1 light year is approximately 9.46 trillion kilometers. Multiply that by 2.537 million, and you arrive at a number so large it ceases to feel like a number at all. Andromeda is the closest large galaxy to our own. Of the roughly 2 trillion galaxies in the observable universe, this is the neighbor, and it takes light 2.537 million years to cross the gap between us. These 2 galaxies are part of a structure called the local group, a gravitationally bound collection of more than 50 galaxies, most of them small, most of them satellites orbiting the 2 largest members. The 2 largest members are Andromeda and the Milky Way. Between them, they dominate the local group. Between them, they are moving toward each other. Tonight, you are in the Milky Way. You are approximately 26,000 light-years from its center, a supermassive black hole called Sagittarius A star, which contains the mass of 4 million suns and sits perfectly still at the core of the galaxy while everything else orbits around it. Your position in the galaxy is in the Orion Arm, a minor spiral arm, a quiet region between larger structures, neither at the dangerous core nor at the thin and empty outer edge. From where you are, the galaxy extends for roughly 100,000 light-years in diameter. It is shaped like a disk, wide and flat, with a bulging center and spiral arms sweeping outward in a pattern visible only from above or below. You are inside it. You cannot see its shape from where you stand. You can only see its edge-on streak across the night sky, the Milky Way as it appears from Earth, a pale band of compressed starlight, the glow of billions of stars seen through billions of light-years of their own galaxy. Above that band, on a clear night, in a dark place, you can find the Andromeda Galaxy. You are lying on a hillside. The grass beneath you is still warm from the afternoon, slowly releasing the day's heat into the cooling night air. The temperature has dropped perhaps 10 degrees since sunset. Above you, the sky has darkened from the deep blue-gray of early evening into something that is not quite black, a very deep saturated darkness, the kind that only appears far from city lights, the kind that makes stars visible down to the 6th magnitude and sometimes beyond. The Milky Way crosses the sky at an angle tonight, a smear of light so familiar you almost stop noticing it, but you notice it tonight. You trace it from the southern horizon upward through Sagittarius, through Aquila, through Cygnus, into Cassiopeia. You are looking along the plane of your own galaxy. You are looking at the compressed light of approximately 300 billion stars. Above Cassiopeia, slightly to the south, you find the constellation Andromeda, 4 stars forming a rough line, dimmer than you expect, and just above the 2nd star in the line, Murik, something that is not quite a star, something blurred at the edges, something soft. That is it. That is the Andromeda Galaxy, Messier 31, NGC 224, the nearest large galactic neighbor, the thing that is coming from 2.537 million light-years away. It appears to the naked eye as a faint oval smear, perhaps 3 times the apparent diameter of the full moon. If your eyes are fully dark adapted and the sky is very clear, most people see it as a faint blob. It appears unremarkable. It appears stationary. It is not stationary. The first hint that something was different about Andromeda came in the early 20th century. Astronomers had been cataloging the spectra of celestial objects, the way different elements absorb and emit light at specific wavelengths, creating characteristic patterns of dark and bright lines that function like fingerprints for the composition of stars and gas clouds. When light from an object moving away from Earth is observed, those spectral lines shift toward the red end of the spectrum. Redshift, the Doppler effect applied to light. When an object moves toward Earth, the lines shift toward blue shift. Almost everything in the observable universe shows redshift. The universe is expanding. Every galaxy beyond the local group is moving away from every other galaxy, carried by the expansion of space itself. Redshift is the norm. Blue shift is exceptional. Andromeda shows a blue shift. It was Vesto Slipher at Lowell Observatory in Arizona who first measured this in 1912. He found that the spectral lines of Andromeda were shifted toward the blue end of the spectrum, indicating approach rather than recession. The measured velocity at the time was approximately 300 kilometers per second, an enormous speed that was at the time the highest velocity ever recorded for any celestial object. Later measurements refined this. The radial velocity, the component of velocity directly toward us, is approximately 110 kilometers per second, but radial velocity only tells you how fast something is moving along the line of sight. The full picture required measuring proper motion, the actual sideways movement of Andromeda across the sky over time. This measurement, using the Hubble Space Telescope, was completed and published in 2012 by Roland Vandermerel and his team. It required tracking the positions of individual stars in Andromeda over the course of years, detecting shifts smaller than 1/10,000th of an arcsecond. The result: Andromeda is not only moving toward us, but moving on a trajectory that will result in a direct merger with the Milky Way in approximately 3.75 to 4.5 billion years. The collision is confirmed, the timeline is set. The only remaining question is what it will look like. You stare at the smudge above Merak. It is 2.537 million light-years away. It is 220,000 light-years in diameter, more than twice the width of the Milky Way, though its outer regions are fainter and harder to detect. It contains an estimated 1 trillion stars, compared to the Milky Way's estimated 300 billion. It is larger. It is older in some ways. Its core is dominated by older, redder stars, while new star formation is lower than in the Milky Way. At its center sits a supermassive black hole designated M31 star, with a mass estimated at somewhere between 100 million and 140 million solar masses, compared to our own Sagittarius A star at 4 million solar masses. Andromeda's central black hole is between 25 and 35 times more massive than ours. Sit with that for a moment. The smudge above Merak. There is something about holding two scales simultaneously: the soft blur you can see from a hillside and the trillion stars inside it, the supermassive black hole at its center, the dark matter halo extending invisibly in every direction, that produces a specific feeling, not quite awe, not quite dread, something between the two, something that has no precise name in English, something that arrives quietly and stays. The Andromeda Galaxy has a companion, two companion dwarf galaxies actually, M32 and M110, both visible in long exposure photographs as faint satellites orbiting the larger structure. These will participate in the collision as well, their small masses caught in the gravitational drama between the two giants. There are also at least a dozen other satellite galaxies associated with Andromeda, most too faint to observe without dedicated telescope time. The Milky Way has its own satellites, the large and small Magellanic Clouds, visible from the southern hemisphere as separate detached patches of the Milky Way, are the most famous. These too are gravitationally bound, These two are part of the larger system. When the collision happens, the entire architecture of the local group will be involved. But it begins with these two, the Milky Way and Andromeda, moving toward each other at 110 kilometers per second, separated tonight by 2.537 million light-years. Let the number settle. 110 kilometers per second sounds fast. It is fast, faster than any spacecraft ever launched, faster than the fastest missile, faster than anything created by human engineering by a factor of 10 or more. And yet at this speed, crossing 2.537 million light-years takes approximately 4.5 billion years. The speed is real. The distance is simply so large that even this speed requires billions of years to cross it. This is the first compression your mind must make tonight. Speed and distance at scales that require geological time to process. You breathe. The hillside is quiet. The temperature continues to drop. Somewhere below you, very faintly, there is the sound of wind moving through grass, a dry, soft sound barely present. The sky above is very dark and very clear. You can see thousands of stars. You can see the Milky Way. You can see Andromeda. Nothing looks like it's moving. Andromeda will not look any different tomorrow night than it does tonight. It will not look any different in 10 years or 100 years. The proper motion measured by van der Morel, the sideways drift of Andromeda across the sky, amounts to roughly 0.000012 arcseconds per year. Over a human lifetime, this is immeasurable without the most sensitive instruments ever built. Over 1,000 human lifetimes, it is still essentially invisible. The motion is real, the collision is real, the confirmation is scientific and precise and peer-reviewed, and it is happening at a speed that is entirely imperceptible to human experience. This is the second compression your mind must make tonight. The collision is happening. It has already begun, in the sense that the trajectory is set and the distance is closing, and yet no human alive tonight, and no human who will ever live, will witness it in any perceptible way. The timescales are simply too long. What you are doing tonight is different. Tonight, you are not watching with eyes, you are listening with something deeper. You are allowing the facts to move at the pace they actually move, across billions of years, across millions of light years, and you are going to stay with that movement, not compress it into a short film or a fast animation, but let it unfold at something closer to its actual scale. The Milky Way extends around you, 100,000 light-years across, 1,000 light-years thick at the disk, thicker at the bulge, where stars pack tightly around the central black hole, in a structure that from above would look like a soft, round glow at the center of a flat pinwheel. You are 26,000 light-years from that center, orbiting it at approximately 220 kilometers per second. Every 230 million years, your position in the galaxy completes one full orbit of the galactic core. The Earth has completed this orbit approximately 20 times since the planet formed. 20 galactic years. In those 20 orbits, continents have moved, oceans have opened and closed, ice ages have come and gone, and the entire history of complex life has unfolded during roughly the last half orbit. The galaxy is rotating right now. You are moving around the galactic center at 220 kilometers per second, which is faster than Andromeda's approach velocity. You are in motion that is so large and so constant that you have no sensation of it at all. Above you, visible and fixed and impossible to feel, the smudge of Andromeda. Moving closer. It has always been moving closer. When the first modern humans stood under a dark sky and looked up and noticed the soft blur in the constellation we now call Andromeda, the galaxy was already closer than it was a million years before that. When the dinosaurs walked this planet and the night sky was dark and filled with the same stars, the smudge was slightly farther away. When the solar system formed from a collapsing cloud of gas and dust 4.6 billion years ago, Andromeda was further still. Time runs one direction, distance runs one direction. The trajectory is what it is. 4.5 billion years from now, the sky will not look like this. The Big Dipper will be gone, or rather, the stars that form it will have moved along their individual paths through the galaxy until the familiar shape is unrecognizable. The constellation Orion, so anchoring and bright, will not exist as a pattern. The belt of Orion, Alnitak, Alnilam, Mintaka, will have drifted. The sky that every human being in all of recorded history has shared, the permanent-seeming vault of stars, is not permanent. The constellations last tens of thousands of years, not billions. The sky you are looking at tonight is already different from the sky the ancient Egyptians saw, subtly but measurably. On the timescale of the collision, the sky tonight is a single frame in a very long film. You breathe. In. Hold. Out. The grass beneath you, the warmth still held in the earth, the cooling air and the dark and the stars. Andromeda above Mirek. There is a kind of peace available in the very large. Not the peace of things being fine. Things are always complicated, always fragile, always uncertain at the scale of a human life. But the peace of perspective, the peace of scale so vast that the usual anxieties simply do not fit inside it, the peace that comes from holding, even briefly, a number like 2.537 million light years, and feeling, somewhere below thought, that your life is very small and very bright and very specific, a particular arrangement of matter and energy that has never existed before and will never exist again. That is not a sad thought looked at correctly. The Andromeda Galaxy is moving toward you at 110 kilometers per second. In 4.5 billion years, the sky will change in ways that no one who has ever lived has seen. Tonight, you are looking at the beginning of that story. It starts here. It starts with a smudge above Mirek on a dark hillside, and it ends with something that astronomers have given the name Milky, a new galaxy formed from the merger of these two, different in shape and composition from both, stranger and quieter, and very, very old. The journey to that end begins now. The sky is dark. The stars are fixed for all the purposes of a human life. Andromeda is barely visible to your adapted eyes. And 110 kilometers passes between you and it. And another. And another. You are watching something happen that is too slow to see and too large to fully imagine and completely, verifiably, scientifically real. Stay with it. The hillside is quiet. The temperature has stabilized at whatever cool it settles into on a clear autumn night, far from city lights. Your breathing has slowed without you noticing. The stars above you are not moving, or they are moving at the rate of one full sky rotation every 24 hours, which your body has already calibrated for, which feels like stillness. The galaxy is rotating. The planet is orbiting the sun. The The Sun is orbiting the galactic center. The Milky Way and Andromeda are falling toward each other through the dark. Everything is in motion. Nothing looks like it's moving. This is where the story lives, in the space between those two facts, in the gap between what is happening and what is perceptible, in the billions of years of change encoded in a faint oval smudge above a star whose name comes from Arabic, cataloged by astronomers who lived and died 1,000 years ago and never knew that the faint thing they were recording was a galaxy containing 1 trillion stars moving toward them at 110 kilometers per second. You know what they did not know. You are lying on a hillside with 4.5 billion years of future stretching out above you, and the smudge above Merak is moving, and the night is very quiet, and there is nowhere else to be right now, and nothing more important to feel than this. The approach continues. The distance closes. Consider the light that left Andromeda 2.537 million years ago and arrived in your eyes just now. That light was emitted by stars, specific nuclear reactions, specific moments of energy release in the cores of suns you will never see individually. By the time that light arrived here, those individual stars have aged. Some have died. The supergiants among them, the brightest, hottest stars, have lifetimes measured in millions of years, which means some of the stars whose light you are seeing tonight no longer exist. You are seeing the afterglow of stars that are already gone. This is true of every object you see in the night sky, to varying degrees. The moon's light is about 1.3 seconds old. Sunlight is about 8 minutes old. Light from Proxima Centauri is 4.24 years old. Light from the Orion Nebula is about 1,344 years old. It left that nebula during the Tang Dynasty in China, before the Norman conquest of England, before the construction of most of the great medieval cathedrals. And the light from Andromeda is 2.537 million years old. Astronomy is the only science where looking outward is the same as looking backward in time. The sky is not a snapshot of the present. It is a layered archive of the past, each object at a different temporal distance, each photon carrying information from a moment that is already gone. This means that the Andromeda you are seeing tonight is not the Andromeda that exists right now, wherever and whatever right now means, across millions of light years. The galaxy you are watching is the galaxy as it was 2.537 million years ago. The actual current state of Andromeda, its exact stellar distribution, its current star formation rate, whether any of its stars have gone supernova in the last 2 million years, is information that has not yet reached Earth. The universe you can observe is always a past version of itself. What exists right now, in the truest sense, at this exact moment across the entire volume of observable space, is unknown and in principle unknowable, because the information about it cannot travel faster than light, and light takes time, and time creates a permanent lag between reality and observation. You are looking at a 537 million year old galaxy that is confirmed to be moving toward a collision with your own. The facts are clear, the trajectory is confirmed, the future is as certain as orbital mechanics can make it. And still, in some deep sense, you are looking at a past that you cannot change, from a present that you cannot fully see, toward a future that none of your species will witness. That is not a sad thought. It is the condition of existing in a universe that is larger than any one perspective can hold. It is the condition of being a temporary arrangement of matter that is, against all probability, capable of understanding its own smallness. You are made of atoms that were forged in stars that died before the solar system formed. You are breathing an atmosphere shaped by billions of years of geological and biological processes. You are lying on a crust of rock that has been moving across a molten interior for 4.5 billion years, and you can look up and recognize, in a faint smudge of light, a galaxy containing 1 trillion stars that is falling toward you. This recognition, the fact of it, the sheer improbability of an arrangement of matter being able to perceive and understand the scale of the universe it inhabits, is perhaps the most remarkable thing in the observable cosmos. More remarkable, in a sense, than the collision itself. The story is only beginning. The hillside is still beneath you. The stars have moved, not by much, not in any way the eye catches easily, but the rotation of the Earth has carried you a few degrees along the arc of the night sky. Andromeda is now slightly higher, slightly past the meridian, drifting westward with everything else in its slow, predictable arc. You are still looking at the smudge above Mirek. You are still watching something that appears to be standing still. Now we begin moving forward, not at the speed of thought that is too fast, too easy, too forgettable. We move forward slowly. We let the science set the pace. The first thing to understand, before the timeline advances even a single step, is what a galaxy actually is. Not what it looks like, what it is. A galaxy is not a collection of stars packed closely together in a glowing cloud. That is what photographs suggest, and photographs are misleading. A galaxy is almost entirely empty space. The stars within it are so far apart, so isolated from one another, that if you were to stand on a planet orbiting any average star in the Milky Way, the nearest neighboring star would appear as nothing more than a bright point of light, close enough to be the brightest star in your sky, but so far away that the fastest spacecraft humans have ever launched would take tens of thousands of years to reach it. The nearest star to our Sun is Proxima Centauri, 4.24 light-years away. That is approximately 40 trillion kilometers. If the Sun were the size of a marble, about 14 millimeters in diameter, and you place that marble on a table, the nearest neighboring marble would need to be placed approximately 4,000 kilometers away to represent the same scale, not 4 meters, not 400 meters, 4,000 kilometers. The distance from Los Angeles to Madrid, from Sydney to Moscow, from one side of a continent to the other. That is the separation between neighboring stars, scaled to the size of a marble. Now fill a volume of space 100,000 light-years across, with marbles at that spacing. That is the Milky Way. Hundreds of billions of tiny points of light, each one separated from its nearest neighbor by the equivalent of 4,000 kilometers in marble scale. Each one an island, each one isolated in an ocean of nothing. When two of those marble-filled volumes drift into each other, when the Milky Way and Andromeda collide, what is actually colliding? Mostly nothing. Two vast collections of nearly empty space, interpenetrating each other, passing through each other. The stars within each galaxy are so small relative to the spaces between them that the probability of any two stars making direct contact during the collision is essentially zero. Astronomers have calculated this carefully. The cross-sectional area of a star divided by the average area of sky available to each star in a galaxy multiplied by the number of close encounters during a galactic collision, gives a collision probability per star of somewhere around 1 in a million billion over the entire course of the merger. The number is so small, it is essentially indistinguishable from zero. Two galaxies will collide, hundreds of billions of stars on each side, and the stars themselves, with overwhelming probability, will never touch. You are still on the hillside. It is still dark and quiet and cold and clear, but something has shifted in the quality of your attention. Something has adjusted. The smudge above Mirek is not a solid object. It is not a wall or a mass or a thing that will impact the Milky Way the way a fist impacts a table. It is mostly space. It is mostly distance. It is mostly the absence of matter arranged in a specific gravitational pattern. And the Milky Way is the same. Two patterns of gravity, each carrying hundreds of billions of stars, each embedded in a dark matter halo far larger than the visible galaxy, falling toward each other across 2.537 million light-years. What will collide, first and most dramatically, is not the stars. It is the dark matter. Dark matter is the name given to a form of matter that does not interact with electromagnetic radiation. It does not emit light. It does not absorb light. It does not reflect light. It cannot be seen. Its existence is inferred entirely from its gravitational effects, the way galaxies rotate, the way galaxy clusters bend the light passing through them, the way the large-scale structure of the universe formed. Approximately 27% of the universe's total energy density is dark matter. Normal matter, the atoms that make up stars and planets and you, accounts for only about 5%. Each galaxy is embedded in a dark matter halo that extends far beyond the visible disk. The Milky Way's dark matter halo reaches outward for perhaps 300,000 to 600,000 light-years in every direction, a sphere far larger than the visible galaxy it surrounds. Andromeda's halo is similarly vast. At the current separation of 2.537 million light-years, these halos are not yet overlapping, but they are approaching, and when they begin to overlap, which will happen long before the visible galaxies come anywhere near each other, the gravitational interaction will begin. This is already happening in slow motion. The outer fringes of the two gravitational systems are already beginning to feel each other, not dramatically, not in any way that would be visible from Earth tonight or next century or next millennium, but the mathematics of gravity does not require proximity the way contact does. Gravity reaches. It falls off with the square of distance, but it never reaches zero. Andromeda is already exerting a gravitational pull on the Milky Way. The Milky Way is already exerting a gravitational pull on Andromeda. They have always been pulling at each other. The pull is what has accelerated them to 110 kilometers per second. The pull is what has set the collision on its confirmed trajectory. This is the force that will reshape the sky. Now we move forward. Not in years, not in centuries, in billions of years, because that is the scale at which this story is told. 1 billion years from now. Your position on the hillside does not change, but above you the sky has changed. Not dramatically. You would need sensitive instruments to confirm what your eyes might only suspect. But the smudge above Mirek is larger. It is no longer quite a point. It has begun to resolve, not into individual stars, not yet, but into a shape that is more obviously structured than the faint oval you saw on your first night. Andromeda is closer. In 1 billion years, the approach velocity has not slowed significantly. The distance has decreased from 2.537 million light-years to somewhere between 1.5 and 2 million light-years, the exact value depending on the precise interaction of the two dark matter halos and the relatively small gravitational perturbations of the other local group members. But the direction is unchanged. The blue shift is still there. The collision is still confirmed. The sky has changed in other ways too. The stars that form the constellations you know or knew on that first hillside night are gone, completely gone, replaced by a sky full of different configurations. The individual stars of Orion have moved along their own orbits. Betelgeuse, which was already in the late stages of stellar evolution on your first night, has long since gone supernova, exploded, collapsed, and left behind either a neutron star or a black hole at the location of what was once one of the brightest stars in your night sky. The Orion Nebula, visible through a small telescope on your first night as a greenish patch of light just below Orion's belt, has continued to collapse and form new stars, some of which have by now lived and died in their own right. The sky 1 billion years from now is not recognizable. The constellations are gone. The familiar anchors of the night sky are gone. Even the Milky Way, the pale band of galactic light that has grounded human vision since before recorded history, looks different. The same spiral structure, but the stars within it have redistributed over 1 billion years of orbital dynamics. And against this unfamiliar sky, Andromeda is noticeably, measurably closer. Your sun is still there. The sun's main sequence lifetime, the period during which it fuses hydrogen into helium in its core, maintaining a stable luminosity and temperature, is estimated at approximately 10 billion years total. The sun formed approximately 4.6 billion years ago. 1 billion years from now, the sun will be 5.6 billion years old, still well within its main sequence, still stable, still burning hydrogen, still providing the energy that, if Earth remains habitable, which is a separate and complicated question, could sustain life. But the sun is not the same as it is tonight. Stars on the main sequence gradually increase in luminosity over their lifetimes as the helium ash accumulates in their cores and the hydrogen-burning shell expands outward. The sun today is approximately 30% brighter than it was when the solar system formed 4.6 billion years ago. 1 billion years from now, it will be approximately 10% brighter still. This gradual brightening has real consequences for planetary habitability. Models of Earth's long-term climate suggest that in approximately 1 billion years, increased solar luminosity will have driven enough additional warming to trigger a runaway greenhouse effect on Earth, not unlike what occurred on Venus long ago, unless other factors intervene. Whether Earth remains habitable in 1 billion years is genuinely uncertain. The science is complex and depends on the long-term behavior of the carbon silicate cycle, the evolution of Earth's geological activity, the reflectivity of the planetary surface and atmosphere. What is not uncertain is that the sun is changing, slowly, continuously. In 1 billion years, a slightly brighter sun will shine on a planet whose habitability is at best marginal. You breathe. The hillside beneath you, the cooling air, the unfamiliar sky. And Andromeda, closer now, its structure beginning to be visible in a way it was not before. 2 billion years from now. This is where the tidal forces begin to become significant. Tidal forces are the differential gravitational pull across an extended object, The side of an object closer to the source of gravity experiences a stronger pull than the side farther away. On Earth, this differential pull from the moon creates the tides of the ocean, the bulge of water on the side of Earth facing the moon, and the corresponding bulge on the opposite side as the moon's gravity differentially stretches the planet. The same physics applies at galactic scales. As Andromeda approaches the Milky Way, the differential gravitational pull across the diameter of the Milky Way begins to distort it. Stars on the side of the Milky Way facing Andromeda are pulled slightly more strongly toward Andromeda than stars at the center or the far side. This creates a stretching effect, a tidal distortion that begins to pull stars toward and away from Andromeda in a pattern that will eventually produce visible streamers. These are called tidal tails. Tidal tails are long filaments of stars pulled out of their host galaxies by differential gravitational forces during close encounters. They have been observed in many interacting galaxy pairs throughout the universe. Some of the most dramatic and beautiful astronomical images ever captured show pairs of galaxies with long, sweeping arcs of stars trailing from them like wings or antennae. The most famous example is the Antenna Galaxies, NGC 4038 and NGC 4039, a pair of colliding galaxies approximately 45 million light-years away in the constellation Corvus. The Antenna Galaxies have been observed in various stages of their merger, and their long tidal tails, which give the system its common name, represent exactly the kind of structural disruption that the Milky Way and Andromeda will experience. 2 billion years from now, the outer regions of the Milky Way are beginning to develop tidal distortions. Stars at the very edge of the galactic disk, in regions where the orbital velocity is lower and the galactic gravity is weaker, are beginning to feel the differential pull of Andromeda. They are not yet forming obvious tails, that will come later, but their orbits are no longer purely governed by the Milky Way's central gravity. Something else is beginning to contribute. From the perspective of a hypothetical observer, anywhere in the Milky Way, 2 billion years from now, Andromeda is enormous. It spans many degrees of sky. It is not a smudge. It is a structure, visible spiral arms, a bright core, the faint glow of its outer halo covering a wide swath of night sky. It is the most dramatic object visible to the naked eye in the entire universe, and it is growing larger. The Sun, 2 billion years from now, is 6.6 billion years old, still on the main sequence, still stable. Luminosity has increased further. The question of Earth's habitability has become more complicated. The geological record of this future Earth, if there is anything to record it, would show a world in transition, with a climate under pressure from a steadily brightening star. But the Sun itself is fine. It has time. Stars have time in a way that human lives do not. A star born when our solar system was born will live for another 5 billion years at least. 5 billion years from now, the Sun will finally exhaust the hydrogen in its core and begin the transition to a red giant, swelling outward, cooling its surface, expanding to perhaps 200 times its current radius, engulfing Mercury, engulfing Venus, possibly engulfing Earth. That transition, the death of the Sun as a main sequence star, will happen at approximately the same time as the collision with Andromeda is reaching its most dramatic phase. These two events are not causally connected. They are simply happening on similar timescales because both are processes that unfold over billions of years, and the universe has been running long enough that many different billion-year processes are underway simultaneously. But their coincidence means that the most dramatic period in the solar system's existence, the death of the sun, will occur against the backdrop of the most dramatic change in the Milky Way's structure in the last several billion years. Two enormous things happening at the same time. The sky above you is completely unfamiliar now. The stars are in configurations that no human being has ever seen, and no human being who has yet lived will ever see. The galaxy is different. The position of the sun within the galaxy is different. Orbital dynamics over 2 billion years do not leave any star in exactly the position it occupied before. An Andromeda. Andromeda is not a smudge anymore. Andromeda is a presence, a structure filling an arc of sky that would astonish anyone who had only ever seen tonight's sky. Its outer halo overlaps with the Milky Way's outer halo now. The dark matter halos of both galaxies are beginning to merge, not in a sharp boundary, but in a gradual interpenetration, a commingling of invisible mass that extends far beyond the visible light of either galaxy. Gravity is doing what gravity does. It is pulling. The differential pull across the disk of the Milky Way is increasing. The tidal distortions that began 2 billion years ago as subtle perturbations are becoming more pronounced. Stars in the outer regions of the galaxy are following paths that are increasingly influenced by Andromeda's presence. The neat mathematical spirals of the galactic arms are beginning to develop irregularities, not chaos, not yet, but the first signs of disruption. And Andromeda is experiencing the same thing. Its outer regions are responding to the Milky Way's gravity. Its shape is beginning to distort. The two galaxies are reaching toward each other in ways that are not yet dramatic, but are completely inevitable. 3 billion years from now. The approach continues. The separation has decreased to perhaps 500,000 to 800,000 light years, down from 2.537 million. Andromeda dominates one entire quadrant of the sky. Its spiral arms are visible to the naked eye of any observer anywhere in the Milky Way. Its core, that bright, compact central bulge, blazes like a second center of the universe, too diffuse to cast shadows, but bright enough to give the night sky a warm, structured glow in the direction of Andromeda. The tidal tails have appeared. Not fully formed yet, the full development of tidal tails requires the closest approach, the point of maximum differential gravity. But streamers of stars are beginning to trail from the outer edges of both galaxies. These are stars that have been gravitationally nudged out of their orbits and are following new trajectories, pulled by the combined gravitational field of two approaching galaxies into paths that take them outside the boundaries of either galaxy. From a distance, these streamers would make the interacting system look something like the antennae galaxies, long sweeping arcs of stars tracing the gravitational sculpture of the encounter. From inside, they would look like regions of sky with unusually high star density, not dramatically so, not like the core, but noticeably, measurably different from the galaxy's average. Throughout all of this, the stars themselves are not colliding. This deserves another moment of attention, because it remains true even as the visual drama increases. The tidal tails are real, the distortion is real. Stars are genuinely being displaced from their orbital paths by gravitational forces that are real and measurable and consequential. And none of them are hitting each other. The marble analogy holds. The spacing between stars is so vast, Proxima Centauri, our nearest neighbor, is 4.24 light years away, which is about 40 trillion kilometers. that even as hundreds of billions of stars from two galaxies are scrambled together and redistributed by tidal forces, the probability of any stellar collision is negligible. What does collide, and dramatically, is the interstellar gas. Unlike stars, the gas that fills the space between stars does interact with other gas during a galactic collision. Gas clouds can collide, they can compress, and when interstellar gas clouds compress, they collapse under their own gravity and form new stars. This is one of the most striking aspects of galactic collisions observed throughout the universe. Merging galaxies produce enormous bursts of new star formation. The antennae galaxies, for example, are forming new stars at a rate far higher than either galaxy would be forming them in isolation. Infrared observations reveal thousands of young star clusters embedded in the interacting region, clusters that did not exist before the collision began. In 3 billion years, as the Milky Way and Andromeda approach first contact, the interstellar gas of both galaxies will begin to compress. New star-forming regions will ignite, enormous clouds of hydrogen collapsing under the pressure of the encounter, producing stars at rates that would be dramatic compared to the galaxy's current star formation rate. New stars, being born from the collision of two galaxies? Blue-white massive stars, burning hot and fast, living only millions of years before exploding as supernovae. Red and yellow stars like the Sun, forming in clusters, settling into long, stable lives. The night sky of anyone inside this system, if there is anyone, if there are planets around these new stars, if those planets have surfaces to stand on and atmospheres to breathe, would be spectacular. Young star clusters blazing, supernovae flashing, the glow of star-forming regions painting the sky in colors that are currently only visible through the infrared detectors of space telescopes. 3 billion years from now, the Milky Way's sky is not the dark, quiet vault you see from your hillside tonight. It is busy, it is luminous, it is in the middle of something. In, hold, out. You are still on the hillside, the night is still quiet, the stars are still. You have moved, in thought, across 3 billion years of future, and the most dramatic event in the history of the Milky Way since its formation is still several 100 million years away. That is the scale. This is not a fast story. It has never been a fast story. The universe does not move at a pace that accommodates human impatience. It moves at the pace that gravity and orbital mechanics and the laws of physics dictate, which is sometimes very fast. A supernova collapses in seconds. A gamma-ray burst releases more energy than the sun will in its entire lifetime in a fraction of a second, and sometimes incomprehensibly slow. A galactic merger is incomprehensibly slow. You are watching it happen in the only way it is possible to watch it, by letting the scale of it settle into you, by allowing the numbers to be as large as they actually are, by not compressing or accelerating or simplifying. The approach continues. 3.75 billion years from now, the separation between the centers of the two galaxies has narrowed to approximately 250,000 light-years. The outer halos are deeply interpenetrating. The tidal tails are pronounced and visible across the sky. The star formation rate in the interacting gas has spiked dramatically. The Sun, now 8.35 billion years old, is beginning to show signs of its eventual red giant transition. Its luminosity increased to perhaps 150% of its current value, its radius slightly expanded. And Andromeda fills nearly a quarter of the visible sky. Not quite first contact, not quite the moment when the centers approach most closely, but close. The gravitational interaction is now the dominant force shaping the structure of both galaxies. Stellar orbits are being disrupted. Stars are being flung outward into the space between the two galaxies on long, looping trajectories that may take hundreds of millions of years to resolve. New stars are forming in the compressed gas. Old stars are ending their lives in supernovae, seeding the interstellar medium with heavy elements that were not there before. The chemistry of the universe is changing. The structure of the two galaxies is changing. The sky everywhere in both systems is changing. And the stars are not colliding. The marble scale spacing holds. The math does not change. The drama is gravitational, not physical. The collision is real and consequential and will reshape everything. And the individual stars, those points of nuclear fire suspended in vast distances of nothing, will pass each other in the dark without touching. Something about this is, when you hold it long enough, profound. Not comforting, exactly, not alarming. Something else, something that sits at the intersection of emptiness and consequence, where the fact that space is almost entirely nothing does not make what happens within it meaningless, but in fact enables it. The emptiness is what allows the movement. The emptiness is what allows the galaxy to pass through another galaxy and survive, distorted, restructured, but continuous. The space between stars is not a failure of structure, it is the structure. You breathe. The hillside is solid beneath you. The temperature is cool. The stars above you are where they have always been, not in the sky of 3 billion years from now, but in tonight's sky, which is your sky, the sky you share with everyone who has ever looked up and noticed the soft blur above Mirak. Tonight's sky is temporary. All skies are temporary. The stars that form the Milky Way's disk will not be in these configurations in 1 billion years. The galaxy you belong to will not have clean spiral arms in 5 billion years. The night sky itself, the concept of a dark background spangled with points of light, will eventually change as the universe expands and the light from distant galaxies redshifts beyond the visible. But none of that is happening tonight. Tonight the sky is what it is. Andromeda is where it is. The hillside is cool and quiet and real, and the stars are in their places, and 4.5 billion years of future are encoded in the soft blur above Mirak, patient and unhurried and completely inevitable. The approach continues. Every second, 110 kilometers. Every year, 3.5 billion kilometers. Every million years, 3.5 trillion kilometers, or roughly a third of a light year. The math is patient. The universe is patient. You are learning to be patient too. Somewhere in the dark above you, in the direction of Andromeda, the dark matter halos of both galaxies are already overlapping. Not in a way that produces any light, any detectable signal except through the most sensitive gravitational measurements. But the overlap is real. The interaction has begun in the language of dark matter, which is the language of mass without light. The visible collision, the moment when the structures that can be photographed and mapped and observed begin to interpenetrate, is still billions of years away from tonight. And from the perspective of the 3 billion year future sky, it is only hundreds of millions of years away. Time is relative to scale. At galactic scales, 100 million years is a brief moment, a small fraction of the time the solar system has existed, a small fraction of the time the Milky Way has been a galaxy. At human scales, 100 million years is a number so large it loses meaning. No individual, no civilization, no species has ever experienced or will ever experience 100 million years. The collision will happen on galactic time, not human time. This is the fundamental strangeness of this story. It is a true story, grounded in precise scientific measurement and confirmed trajectory. It will happen exactly as described, to the best of our current understanding of gravity and galactic dynamics, and it is entirely outside the scale of human experience. The only way to approach it is the way you are approaching it now, lying on a hillside, breathing slowly, letting the numbers be as large as they are, watching the smudge above Mirek with the knowledge of what it contains and where it is going. The sky is dark. The stars are still. And in the quiet that follows understanding something very large, your body has been settling towards sleep without you noticing. The hillside beneath you is a fact. The cooling air is a fact. The stars above you are facts, every one of them, a specific temperature, a specific mass, a specific distance, a specific age, a specific fate. The universe is made of facts arranged in an order that has produced, among other things, a hillside on a planet orbiting a star, and you on that hillside, breathing, looking up, understanding across the distance of 2.537 million light years that something is coming. Something has always been coming. The sky is dark, the stars are still. Andromeda is where it has always been, above Mirek, patient and real, and closer than it was when the first human eyes found it. Closer, always, by 110 kilometers every second. The approach does not stop when you close your eyes. The math does not pause for sleep. The universe continues at its own pace, on its own timescale, moving through processes that began before the Earth existed and will continue long after the solar system is gone. You can rest inside that continuity. The hillside holds you. The galaxy holds the hillside. The local group holds the galaxy. Gravity holds all of it. The fundamental force, the one that never turns off, the one that has been pulling Andromeda toward you for as long as both galaxies have existed. Breathe. Every second, 110 kilometers. The stars are still. Sleep is not far. The sky has changed. Not in the way a storm changes a sky or the way sunrise changes it, not in any time frame that resembles human experience. But if you could hold your position on this hillside and let the billions of years move past you like weather, this is what you would see. Andromeda has arrived. Not arrived in the sense of landing, or stopping or completing a journey. Arrived in the sense that it is no longer a smudge, no longer a feature you have to know where to look to find. It fills the sky in front of you in a way that has no equivalent in the night you began with, no analog in any sky that any human being has ever seen. The closest approach is near. We are approximately 3.75 to 4 billion years from the night you first lay on that hillside. The separation between the two galactic centers has narrowed to somewhere around 100,000 light years, down from 2.537 million. The dark matter halos of both galaxies have been deeply interpenetrating for hundreds of millions of years. The outer stellar populations have been exchanging material through tidal disruption for longer still. What was once a boundary between two separate systems is now a gradient, a blurring of identity, a region where it is genuinely difficult to say which stars belong to which galaxy. The first pass is beginning. This is the moment astronomers refer to when they describe the collision, not the slow approach across billions of years, not the gradual tidal distortion, the first pass, when the central bulges of the two galaxies sweep through each other at high velocity, when the gravitational interaction is at its most intense, when the sky transforms in a way that would be unmistakable to any observer anywhere within either system. You are going to be inside it. The sky above you is not dark tonight. That is the first thing to understand. The concept of a dark night sky, a black background with points of light, has changed. The background of the sky in the direction of Andromeda is not black. It is filled with diffuse light. The outer halo of Andromeda, which contains billions of stars too faint to see individually, but numerous enough to create a continuous low-level glow, covers more than 90 degrees of sky, from horizon to nearly overhead. In one entire half of the night, the sky has a luminosity that has no equivalent in the sky you first saw from this hillside. And it has structure. Spiral arms, not the tight, geometrically perfect spiral arms of a textbook diagram. Those exist only in galaxies seen from the outside, at distances measured in millions of light years, where the entire structure can be taken in at once. What you see from inside is different. What you see is a band of stars, denser than the background, curving across the sky in an arc that is clearly not random, clearly organized by some gravitational logic that your eye follows even if you cannot name it. You are seeing a spiral arm of Andromeda from within the collision zone, and it looks like the Milky Way looks from Earth, a streak of concentrated starlight across the dark, except brighter, closer, and angled differently from the Milky Way's own band. Two galactic planes crossing each other in the sky. Two rivers of starlight, one your own galaxy's disk, one Andromeda's, intersecting at an angle that creates a cross of light across the entire visible sky. This is real. This is what the sky will look like during the first pass, based on simulations published by NASA and multiple independent research groups, based on the measured trajectory of the approach, based on the confirmed geometry of the collision. You are standing inside it now. The interstellar gas is where the drama concentrates. The math that protected every star during the slow approach has not changed. The distances between stars, those 4 light-year scale separations, those 4,000-kilometer marble gaps, remain exactly what they were. Stellar collisions during the merger are still essentially impossible, even now, even here, at the moment of maximum gravitational intensity. But gas does not behave like stars. Gas is not a collection of discrete, isolated objects separated by vast distances. Gas is a medium, a continuous material that fills the space between stars, varying in density and temperature and chemical composition, but present throughout the galactic disk in a way that allows it to interact with other gas when two galactic disks collide. The interstellar medium of the Milky Way is a complex environment. It contains molecular clouds, the densest regions, cold and dark, primarily molecular hydrogen, where new stars form. It contains diffuse atomic hydrogen, warmer and more spread out. It contains hot, low-density plasma created by supernova explosions, filling large bubbles in the galactic disk. It contains dust, tiny solid particles of silicates and carbon compounds and ice-coated grains that absorb and scatter starlight, creating the dark patches visible in photographs of the Milky Way. All of this material, the molecular clouds, the diffuse gas, the dust, is now colliding with the corresponding material in Andromeda. When two gas clouds collide, they do not pass through each other the way stars do. They compress. The kinetic energy of the collision is converted to heat and pressure. Dense regions become denser. Molecular clouds that were stable, gravitationally balanced between internal thermal pressure and self-gravity, are no longer stable. The compression from the collision tips the balance. Self-gravity wins. The clouds begin to collapse. Collapsing gas clouds form stars. This is the process, the Jeans instability, named for James Jeans, who described the mathematics in 1902, by which all stars in the universe form. A region of gas reaches a density and mass above which thermal pressure can no longer support it against its own gravity. It collapses. As it collapses, it fragments. The fragments collapse further. Eventually, each fragment becomes dense enough and hot enough that hydrogen fusion ignites in its core, and a new star is born. During the first pass of the galactic collision, this process is happening across an enormous scale. Millions of new stars, forming simultaneously, scattered through the collision zone, not over billions of years, as star formation normally proceeds in a stable galaxy, concentrated in a burst that the collision has triggered, a wave of star birth driven by the compression of gas that would never have collapsed on its own without this encounter. The most massive of these new stars burn hot and bright and blue. Their surface temperatures may reach 30,000 to 50,000 Kelvin, compared to the Sun's surface temperature of approximately 5,778 Kelvin. They are luminous, some of them millions of times brighter than the Sun, and their lifetimes are correspondingly short. A star 20 times the mass of the Sun may live only a few million years before exhausting its fuel and dying in a supernova explosion. On the timescale of the galactic collision, these stars are born and die almost instantaneously. But while they live, they are brilliant. The star-forming regions lit by these massive young stars, HT regions, named for the ionized hydrogen that makes them glow, are among the brightest features in any galaxy. The Orion Nebula, which you could see as a faint smudge in Orion's sword on your first hillside night, is an HT region. At 1,344 light-years, it appears small and faint. The star-forming regions triggered by the galactic collision are far larger, far more active, and spread across the collision zone in patterns that would light the sky from within. You are not looking at a dark sky spangled with points of light anymore. You are looking at a sky that is luminous, structured, active. In the direction of the collision zone, which is now everywhere because you are inside it, there are knots of brightness that mark new star clusters. There are diffuse glows from ionized gas clouds. There are the winding structures of tidal tails, rivers of stars pulled from their original positions and thrown into new trajectories, some of them arcing far above and below the plane of either galaxy. And somewhere in all of this, the Sun. The Sun is now between 8.6 and 9 billion years old. Its main sequence lifetime is almost over. The hydrogen in its core has been steadily depleting for nearly 9 billion years. The core is shrinking under its own gravity, heating up while the hydrogen-burning shell around it expands. The Sun's outer envelope is beginning to respond, puffing outward, cooling at the surface, shifting in color from yellow-white toward orange. The Sun is in the subgiant phase, not yet a red giant, but no longer what it was on your first night. It is larger, perhaps 50% larger in radius than tonight's sun. It is cooler at the surface. It is significantly brighter, perhaps 2 to 3 times the luminosity of tonight's sun. This increased luminosity has had consequences for the inner solar system. Venus, if any of its surface features survive at all, is now hotter than it was. Earth's atmosphere and surface have been subjected to a slow, steady increase in solar radiation over billions of years, and the question of habitability has long since become academic for the purposes of this story. What matters is that the sun is still there, still fusing, still orbiting the galactic center. Though the galactic center at this point in the collision is not the neat, well-defined structure it was on your first night. The rotation of the Milky Way has been disrupted. Stars are following new orbits, shaped by the combined gravitational field of both galaxies. The sun's orbit is not what it was. Where exactly the solar system is located within the collision zone depends on simulations that carry inherent uncertainty, the exact geometry of the first pass, the exact mass distribution of dark matter in both halos, the precise trajectory of the approach. Different simulations produce different outcomes for individual stars, but in the aggregate, the behavior is predictable. Stars near the outer edge of the Milky Way's disk are more susceptible to tidal disruption, more likely to be thrown into new orbits or into the tidal tails. Stars near the center are more gravitationally anchored, more likely to remain in something resembling their original orbits. The sun is at 26,000 light-years from the galactic center, neither the outermost nor the innermost region, but a middle position that various simulations treat differently. Some place the solar system in a region that is relatively undisturbed during the first pass. Others suggest it is displaced significantly. The uncertainty is honest. The system is chaotic at this level of detail, sensitive to initial conditions in ways that make precise prediction impossible for individual stars. What is certain is that the sun survives the first pass. The first pass does not destroy stars. It disrupts orbits. It compresses gas. It triggers star formation. But the stars themselves, those tiny, isolated nuclear furnaces, separated by 4 light-year scale distances from their neighbors, pass through the encounter intact. The marble spacing holds. Even here, even at the moment of maximum drama, when the centers of 2 galaxies are sweeping through each other, when the sky is full of tidal tails and star-forming regions and the crossed bands of 2 galactic planes, even here, the stars are not touching. Take a moment with that. The entire visual spectacle of the collision, the tidal tails stretching across the sky, the blue-white fire of new star clusters, the crossed rivers of galactic light, is happening in the context of an event in which the fundamental units of the galaxy, the stars themselves, are not interacting directly at all. The drama is gravitational and gaseous. It is a drama of geometry, of orbital mechanics, of compression and collapse. The stars are passive participants, moved by forces they generate but do not feel the way matter feels, a direct impact. You breathe? The sky above you is extraordinary. There is no other word for it. 2 spiral galaxies interpenetrating each other, their combined light filling the sky from horizon to horizon, their star-forming regions igniting in knots of blue and white, their tidal tails arcing into the space around them like the wings of something impossibly large. And in the middle of all of it, a sound that you are not hearing but that the universe is producing regardless: gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. produced by the acceleration of massive objects. They were predicted by Einstein's general theory of relativity in 1916 and first directly detected by LIGO in September 2015, a moment that opened an entirely new way of observing the universe. The waves detected by LIGO came from the merger of two stellar mass black holes, objects of tens of solar masses. The waves they produced were extraordinarily faint by the time they reached Earth, stretching and compressing the detector by a distance smaller than 1,000th of the diameter of a proton. Galactic scale mass produces galactic scale gravitational waves. As the centers of the two galaxies sweep through each other during the first pass, the supermassive black holes at their cores, Sagittarius A star and M31 star, are still separated by a significant distance. They have not yet begun to orbit each other directly, but the disruption of the galaxy around them, the redistribution of enormous amounts of mass, the acceleration of hundreds of billions of stars into new orbits, all of this produces gravitational waves at frequencies and amplitudes that are simply beyond the capabilities of any detector currently imagined. The universe is vibrating at a frequency so low that a single cycle takes millions of years, in an amplitude that is enormous at galactic scales, but diluted by distance to invisibility by the time it reaches any observer outside the local group. The gravitational waves of the galactic merger are real. They are physical. They propagate outward through space-time at the speed of light, and they are completely imperceptible to any instrument yet conceived. The universe is full of things that are real and completely imperceptible. This is one of them. You stand on whatever ground exists beneath your feet in this sky, because the hillside, the specific hillside of your first night, is almost certainly not the hillside of billions of years from now. And the sky is full of light and structure and drama, and the universe is vibrating at frequencies no instrument will ever measure, and stars are being born and dying, and the sun is in its subgiant phase, and the two galactic centers are somewhere in the middle of their first pass, and none of this is metaphor. Every word of it is real. The first pass does not last long by galactic standards. The two galactic centers sweep through the interaction region and continue. Momentum carries them past each other. The centers separate again. If you could watch the entire event compressed into a minute, it would look like two slow-motion waves passing through each other, distorting as they pass, leaving both changed but continuous. After the first pass, the two galactic centers move apart again, but they do not move very far. The gravitational binding between them, the mutual attraction of hundreds of billions of solar masses on each side, is enormous. The kinetic energy of the first pass is not enough to escape that binding. The two systems slow, decelerate, and begin to fall back toward each other. The second collision is coming. But first, a pause, a moment between events. The two galactic centers have separated again, perhaps by 50,000 to 100,000 light years, and the system is catching its breath in the only way astronomical systems can, by continuing the same physics it has always used, just in a new configuration. The sky during this interlude is spectacular in a different way. The tidal tails are at their most extended, long arcs of stars trailing from both systems, curved by the gravity of the encounter into shapes that, from outside, would look like the antennae galaxies, like NGC 3256, like any of the dozens of interacting galaxy pairs captured by Hubble over the decades that astronomers have used as reference points for understanding what the Milky Way Andromeda merger will look like. From inside, the tidal tails look like rivers. Not rivers in the sense of something moving fast. The stars in a tidal tail are moving, of course, following their disrupted orbits at the velocities characteristic of galactic dynamics, hundreds of kilometers per second in some cases. But the density of the tidal tail against the background of space creates a visual impression of a stream, a flow, a concentration of light that curves across the sky in a way that suggests direction and movement, even when observed over timescales too short for any motion to be perceptible. New star clusters dot the tidal tails. The gas compressed during the first pass is still collapsing, still forming stars in the regions where the collision was most intense. The most massive of those new stars have already died. They lived only millions of years, which on the time scale of the merger is nearly instantaneous, and their supernovae have enriched the surrounding gas with heavy elements, carbon, oxygen, silicon, iron, all the elements above helium that can only be produced in stellar interiors and released by stellar death. The chemistry of the galaxy is more complex now than it was on your first night. Every generation of stars enriches the interstellar medium with heavier elements. Every supernova seeds the surrounding gas with the products of nucleosynthesis, the process by which atomic nuclei are built up from lighter elements inside stellar cores, enduring the explosive deaths of massive stars. The galactic merger, by triggering a burst of new star formation and the corresponding burst of supernova deaths, accelerates this chemical enrichment. The next generation of stars to form in this region will form from gas that is richer in heavy elements than the stars forming before the collision. The universe is building complexity. Slowly, over billions of years, through the deaths and rebirths of stars, through the collisions of galaxies, through the compression and collapse and ignition that has been happening since the first stars lit up in the young universe. The chemical complexity of the cosmos has been increasing. The first stars contained only hydrogen and helium. The stars forming in the tidal tails of the Milky Way Andromeda merger contain silicon and calcium and iron in their cores, these elements woven into their structure before they even ignited. Carbon, the basis of organic chemistry, the backbone of every living molecule. Forged in stellar cores, released in stellar deaths, incorporated into new gas clouds, into new stars, into the planets that may form around them. You breathe. The sky is full of new stars being born from the compressed gas of two colliding galaxies, and somewhere in the chemistry of that gas is the carbon that makes breathing possible, the oxygen that makes it necessary, the nitrogen that dilutes the atmosphere into something survivable, all of it forged in previous generations of stars, all of it cycling through the galaxy in the endless pattern of stellar birth and death that has been running since before the solar system existed. The galactic merger is not separate from the chemistry of life. It is part of the same continuous process. The tidal tails arc across the sky. The star-forming regions glow in wavelengths that span radio to ultraviolet. The two galactic centers, having passed through each other, are now separated again, slowing, beginning to fall back. The second collision will be more complete than the first, slower, deeper, more thoroughly mixing the stellar populations of both galaxies. But that comes next. For now, there is this extraordinary sky. The sky that no human has ever seen, and no human who is alive tonight will ever see. This sky that is the confirmed, calculated, peer-reviewed consequence of the smudge above Merak, of the blue-shifted spectral lines that Vestos Slipher measured in Arizona in 1912, of the proper motion that van der Morel's team extracted from years of Hubble observations. This sky is the future of the smudge, and you are inside it. There is another thing happening in the collision zone that is easy to overlook when the visual drama of tidal tails and new star clusters commands the attention, something quieter and more consequential in the long run. The magnetic fields of both galaxies are interacting. Galaxies are magnetized. The Milky Way possesses a large-scale magnetic field that threads through the galactic disk with a strength of a few microgauss, extraordinarily weak by the standards of any laboratory magnet, but sustained across volumes of space so enormous that its total energy is significant. This magnetic field is generated and maintained by the same rotating, turbulent interstellar plasma that produces magnetic fields in stars, a galactic-scale dynamo driven by the differential rotation of the disk and the turbulence injected by supernova explosions. When two magnetized galaxies collide, their magnetic fields interact. The collision compresses and amplifies the magnetic field in the regions where gas is densest. Observations of merging galaxies throughout the universe show enhanced magnetic field strengths in the collision zones, measured through the polarization of radio emission from relativistic electrons spiraling around the field lines. The amplified magnetic field plays a role in the dynamics of the compressed gas, affecting the rate at which gas clouds collapse to form stars, channeling the flow of material in the collision region, participating in the complex interplay of gravity and gas dynamics that makes galactic mergers so difficult to model precisely. The universe is not only gravity and light, it is also magnetism, threaded through the collision zone, invisible and immeasurable without instruments that do not yet exist in the sky above your first hillside, but real and consequential, shaping what forms and where. You are breathing inside a magnetized collision. Your breathing has slowed. The pace of the narration has slowed with it. The events being described are separated by hundreds of millions of years. Years that are passing in this telling, in the space between sentences, in the pause between one breath and the next. The tidal tails catch the light of new stars. The sky is luminous. The two galactic centers are falling back toward each other. And in the quiet between moments, something that has no name in the language of physics settles around you. The feeling of being inside a process that is larger than any category human thought has created, larger than disaster, larger than creation, something that is both at once, something that is simply the universe doing what the universe does, which is to change, always, at every scale, in every direction, without pause and without end. The sky is extraordinary. The stars are not touching. Something vast and quiet is settling around you. Let it. The two galactic centers have been falling back toward each other for hundreds of millions of years. This is the second pass, the final pass, the one that does not end with separation. Everything that the first pass started, the second pass completes. The tidal tails that formed during the first encounter are still there, long arcs of stars distributed through the space around the collision zone, following orbits that are now governed by the combined gravitational field of both systems. The star-forming regions triggered by the first gas compression have had hundreds of millions of years to evolve. Their most massive stars have died. Their medium-mass stars, stars like the Sun, are still burning or are beginning their own final phases. Their lowest mass stars, the red dwarfs that burn so slowly they will outlast everything else in the galaxy by trillions of years, are still in their infancy. The second pass brings the galactic centers to within tens of thousands of light years of each other. The gravitational interaction is now at its most intense. The combined mass of both systems, hundreds of billions of solar masses of stars, plus the much larger mass of dark matter in both halos, plus the mass of the remaining interstellar gas, is pulling everything toward a common center of gravity that does not yet exist but is being created, moment by moment as the merger proceeds. The sky has changed again. The two galactic planes which crossed each other at an angle during the first pass are now more deeply mixed. The distinction between Milky Way stars and Andromeda stars, which was never visible to the eye, which could only be tracked by detailed spectroscopic analysis of stellar velocities and chemical compositions, is becoming meaningless in a spatial sense. Stars from both galaxies are occupying the same regions of space. Their orbits are interleaved. The concept of belonging to one galaxy or the other is dissolving. This is what a merger is. Not a collision in the sense of two objects hitting each other, not a destruction, a dissolution of identity. Two separate gravitational systems gradually surrendering their individual structures to a combined structure that is neither one nor the other, but something new. The new thing is called Milky. This name, a portmanteau of Milky Way and Andromeda, was coined by astronomers as a shorthand for the merged galaxy that will result from the collision. It has no official designation yet, because it does not yet exist, but the physics of what it will be is predictable from the physics of galactic mergers observed throughout the universe. Milky will be an elliptical galaxy, not a spiral. This matters. The Milky Way and Andromeda are both spiral galaxies, disc-shaped structures with winding arms, flat profiles, organized rotation, active star formation. Elliptical galaxies are different in almost every way. They are roughly spherical or ellipsoidal in shape. They have no disk, no spiral arms, no organized rotation. Their stars move in a complex three-dimensional distribution of orbits that do not share a common plane or a common direction. Star formation in elliptical galaxies is very low compared to spirals. The interstellar gas has been consumed or expelled, and without dense gas clouds, new stars cannot form. Elliptical galaxies are quiet. The transformation from spiral to elliptical during a merger is well understood from observations. Galaxy mergers are common throughout cosmic history, and the results have been documented extensively. When two spiral galaxies collide, the organized rotation of each, the galaxy's spin, the correlated orbital motion of its stars, is disrupted by the gravitational chaos of the encounter. Stars that were following circular orbits in a flat disk are deflected into new orbits that are inclined, elliptical, randomly oriented relative to the original disk plane. The ordered rotation is replaced by something more like a swarm, stars moving in every direction, bound by the combined gravity of the system but not following any coherent pattern. The spiral arms disappear. Not suddenly, not in a single event, but over the hundreds of millions of years of the merger. The conditions that maintain spiral arm structure, the organized rotation, the density waves, the fresh supply of gas, are disrupted. The spiral pattern cannot maintain itself in the turbulent, three-dimensional gravitational environment of the merger. What remains after the settling is the smooth, featureless ellipsoid of the merged galaxy. Milky. The sky during the second pass is even more extraordinary than during the first. If extraordinary is a word that still retains meaning after everything that has come before, the mixing of stellar populations has created a sky in which stars from two formerly separate galaxies are distributed in all directions. The organized band of the Milky Way, the pale strip of galactic light that oriented every human who ever looked up at a truly dark night sky, is gone. Its stars have not gone anywhere, but they are no longer organized into a disk structure that produces a distinct band across the sky. They are redistributing slowly into the three-dimensional swarm that will eventually be Milky. The sky is full of stars in all directions. Not the dark sky of your first hillside night, where stars were present in abundance, but still set against a background of deep black. The sky of the merger is brighter in a diffuse, omnidirectional way. Stellar density is higher in the regions where the merging has concentrated stars. The core of the emerging Milky, the combined central bulge where both galactic nuclei are approaching each other, is bright enough to cast faint shadows, a glow in one part of the sky that has no equivalent in any sky that has ever been visible from Earth. At the center of that glow, something unprecedented is happening. Sagittarius A star, the Milky Way's central black hole, 4 million solar masses, and M31 star, Andromeda's central black hole, 100 to 140 million solar masses, are approaching each other. They have been approaching each other since the collision began, carried toward each other by the gravitational dynamics of the merging galaxies. During the first pass, they were still separated by tens of thousands of light years. Now, deep in the second pass, that separation has shrunk to thousands of light years, still vast by human standards, still too large for any direct interaction between the two black holes themselves, but close enough that the dynamics of their mutual approach are beginning to dominate the core of the forming Milky. Black holes do not emit light. They are defined by their event horizons, the surfaces of no return, the boundaries within which the escape velocity exceeds the speed of light. Sagittarius A star has an event horizon radius of approximately 12 million kilometers, or about 17 times the radius of the Sun. M31 star, being 25 to 35 times more massive, has an event horizon proportionally larger. These are enormous objects by human standards. By the standards of the galaxy, they are invisibly small, points of curvature in space-time, surrounded by the complex dynamics of stars and gas that orbit them. As the two black holes approach each other, they will form what astronomers call a binary system, two massive objects orbiting each other. The process by which a binary black hole system shrinks its orbit and eventually merges is complex and involves multiple physical mechanisms. Initially, the two black holes lose orbital energy through a process called dynamical friction, the gravitational drag created by the distribution of stars around them. Stars that pass near the binary are accelerated by the gravitational interaction, and in receiving this energy, they carry it away from the binary system. Each such interaction slightly reduces the orbital energy of the two black holes, causing them to spiral slightly closer together. This process is efficient when there are many stars available to carry away the energy, but as the binary shrinks, it ejects stars from the region around it, depleting the supply of stars available for further dynamical friction. This creates what is called the final parsec problem, a theoretical bottleneck in which the binary black hole stalls at separations of about 1 parsec, 3.26 light years, because it has run out of stars to interact with. Various physical mechanisms have been proposed to resolve the final parsec problem and allow the binary to continue shrinking. Gas dynamics, the inflow of gas from the surrounding galaxy, can carry orbital angular momentum away from the binary. The three-dimensional distribution of stellar orbits in an elliptical galaxy, which includes orbits that pass very close to the galactic center, may provide a continued supply of stars for dynamical friction interactions. The precise mechanism is still an active area of research. What is not in question is the eventual outcome. The two black holes will merge. When two black holes merge, they produce the most powerful gravitational wave event in the universe, not the faint chirp of two stellar mass black holes, which is what LIGO detected, a signal that lasted fractions of a second and required detectors capable of measuring displacements smaller than a proton. The merger of Sagittarius A star and M31 star will produce gravitational waves that carry energy equivalent to a fraction of the total rest mass energy of both black holes, in this case, a significant fraction of the mass energy equivalent of tens of millions of suns, radiated as gravitational waves in a final burst that lasts seconds to minutes. The resulting merged black hole will have a mass slightly less than the combined mass of both progenitors. Some mass will be radiated away as gravitational waves. It will be spinning rapidly, the final spin state determined by the angular momentum of the merging binary, and it will settle in the center of Milkomeda as the new galactic nucleus, the gravitational anchor of the merged galaxy. A single supermassive black hole, more than 100 million solar masses, at the center of a new elliptical galaxy. In what was once the local group of more than 50 galaxies, most of which will eventually be absorbed into Milkomeda over the following billions of years. You breathe. The merger is not complete. These processes, the binary black hole in spiral, the final merger, the settling of the stellar population into the smooth ellipsoidal distribution of an elliptical galaxy, take hundreds of millions to perhaps a billion or 2 years after the second pass to complete. The second pass is the turning point, not the conclusion. But the conclusion is now certain in a way that even the approach was not. Once the two galactic centers have passed each other a second time, the gravitational binding is too strong for any escape. Both systems are committed. The outcome is determined. The sky continues to evolve. The star-forming regions that blazed so brightly during the first pass, those knots of new star formation triggered by the compression of interstellar gas, are fading. Not because the stars formed there are dying, but because the supply of compressible gas is running low. The collision has used up much of the interstellar gas in triggering the burst of star formation. What remains is hotter, more diffuse, harder to compress into the cold, dense clouds that are necessary for new star birth. Elliptical galaxies are red. This is a consequence of their stellar population. Without ongoing star formation, the hot blue-white massive stars are not being replenished. They live short lives and die. What remains are the longer-lived stars, the medium-mass yellow and orange stars like the Sun, and the low-mass red dwarfs that will burn for trillions of years. The average color of the galaxy shifts toward the red end of the spectrum as the massive blue stars die and are not replaced. Milkomeda will be redder than either of its progenitors. Older in its light, quieter in its dynamics, more settled. There is something in this trajectory, from the organized spirals through the chaos of the merger to the quiet ellipsoid of the result that follows a recognizable arc, not the arc of human narratives, not tragedy or triumph, but something more neutral and more vast, a process that moves through disruption to a new equilibrium, a structure that absorbs enormous change and arrives, eventually, at something stable. The universe has no preference for one state over another. Spirals and ellipticals are both valid configurations of matter and gravity. The spiral structure of the Milky Way is not more natural or more correct than the elliptical structure of Milky. They are different equilibria, arrived at through different histories, sustained by different physical balances. But there is something that the human mind notices and cannot quite name in the progression from the active, star-forming gas-rich spiral to the quieter gas-poor, smoothly aging elliptical, something that resembles the passage from one phase of life to another, something that is not metaphor, but is available to the imagination in the way that only true things are. The Sun, during the merger, is in its final phase. The Sun's red giant expansion has been underway for some time at this point. Billions of years have passed since the subgiant phase you witnessed during the first pass. The Sun is now very different from the star you circled on your first hillside night. Its radius has expanded enormously. Models suggest that the Sun will eventually expand to perhaps 200 times its current radius during the red giant phase, though the exact final size depends on mass loss processes that are complex and not perfectly constrained. Mercury has been engulfed. Venus has been engulfed, or at least severely affected. Earth, if it has not already been swallowed, exists in conditions utterly different from those of tonight. Eventually, the Sun will exhaust the hydrogen in its shell and transition to helium fusion in the core. The helium flash, a rapid ignition of helium burning that releases an enormous burst of energy in a very short time. After the helium flash, the Sun will settle into the horizontal branch, a more stable but shorter phase of helium core burning. Then the helium will be exhausted, the core will contract again, and the Sun will ascend the asymptotic giant branch. Another expansion, another period of instability, during which the Sun will shed its outer layers in a series of thermal pulses. The shed outer layers will form a planetary nebula, a glowing shell of gas illuminated by the ultraviolet radiation of the hot stellar core left behind. The nebula will expand outward into the surrounding space, a beautiful, brief structure that will disperse into the interstellar medium over tens of thousands of years. At the center of the planetary nebula, the remaining stellar core, a dense ball of carbon and oxygen, no longer fusing, no longer generating energy by nuclear reactions, supported only by the quantum mechanical pressure of electrons, is a white dwarf. The Sun's white dwarf will be approximately the size of Earth. Its mass will be roughly half the Sun's current mass. The rest was shed in the planetary nebula phase. Its surface temperature will initially be extremely high, tens of thousands of Kelvin, and it will cool slowly, over billions of years, as it radiates away its stored heat. The Sun will end as a cinder, a white dwarf, slowly cooling in the space around the forming Milky, no longer fusing, no longer shining by nuclear fire, but still physically present, still gravitationally participating in whatever structure it finds itself in. This too is real. This too is confirmed by stellar evolution models, by the observation of white dwarfs throughout the galaxy, by the physics of nuclear burning and electron degeneracy that has been tested and validated across decades of astrophysical research. There is no hillside anymore, not in any meaningful sense. Whatever surface existed on whatever planet is present in this system at this stage in the story is a planet that has been transformed by billions of years of geological, biological, and stellar evolution in ways that are genuinely difficult to predict. The specific hillside of your first night is gone, eroded, subducted, redistributed, long before this moment. But you are here in thought. You are here in the way that understanding is a form of presence. You are here the same way that the light from Andromeda was always here, carrying information across 2.537 million light years to land on a hillside where you could receive it. The merger continues. Milky is taking shape. The smooth three-dimensional distribution of stars that characterizes an elliptical galaxy is emerging from the chaos of the collision. The tidal tails that were so prominent during the first pass are being reabsorbed, their stars following orbits that bring them back into the main body of the merged galaxy, or being captured into the growing Milky structure. The boundaries that once defined two separate galaxies are gone. There is one galaxy now, not two, one. In the center of that one galaxy, two supermassive black holes are spiraling toward each other. The gravitational waves they produce are propagating outward at the speed of light in every direction. By the time those waves reach the edge of what was once the local group, they will be too faint to detect by any instrument conceivable, but they are real. They are physical. They are carrying information about the merger of Sagittarius A star and M31 star to the rest of the universe. The universe knows what is happening. It always knows, in the only way the universe knows anything, through the propagation of physical signals at the speed of light or below, through the slow exchange of gravitational and electromagnetic information across the vast distances between structures. Somewhere in the elliptical body of the forming Milky, the sun's white dwarf continues to cool. The planets, whatever remains of them, orbit at whatever distances they have been settled into by the stellar evolution that preceded this moment. The solar system is physically intact, in the sense that the sun's gravity still holds its remnants together, but it is not the solar system of tonight. It is the residue of the solar system. And yet, the atoms are the same. The carbon in the sun's white dwarf was forged in the sun's core during the helium-burning phase. The oxygen was forged there too. These are the same atoms that were in the sun on your first hillside night, rearranged by nuclear reactions, redistributed by mass loss, but present, continuous. The atoms of the solar system do not disappear when the sun stops fusing. They redistribute. Everything redistributes. Nothing is lost at the level of matter and energy. The universe is conservative in the most fundamental sense. Energy is conserved. Mass energy is conserved. Momentum is conserved. The basic accounting of physics holds at every step. What changes is arrangement. What changes is structure. What changes is the specific configuration of matter and energy that produces for a while a star, and then a red giant, and then a white dwarf, and then eventually something cooler and darker. Milky is settling. The sky is quieter now than it was during the first pass. The burst of star formation has subsided. The new stars formed in the collision-triggered bursts are aging. The most massive have been gone for billions of years, their supernova remnants long since dispersed into the interstellar medium. The medium-mass stars are beginning to evolve off the main sequence. The red dwarfs are just entering the long, slow middle of their lives, which will extend for trillions of years beyond this moment. The sky of Milkomeda is an aging sky, still full of stars, billions of them, the combined stellar populations of what were once two galaxies, but no longer the active, star-forming, gas-rich sky of the Milky Way at its peak. A quieter sky, a redder sky, a sky full of older light. There is beauty in older light. Not the electric blue-white of young massive stars, burning through their fuel in millions of years, brilliant and brief. The beauty of older light is different, deeper, more continuous, the accumulated shine of stars that have been burning for billions of years, orange dwarfs and red giants, and the faint persistent glow of stars that have been at this for so long that the concept of beginning is irrelevant to them. Milkomeda is full of this light. And in the center, where the two supermassive black holes are approaching their final merger, there may be a quasar. Quasars, quasi-stellar objects, are among the most luminous objects in the universe. They are powered by supermassive black holes actively accreting material, gas and dust and disrupted stars falling into the black hole, heated by the accretion process to temperatures so high they emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays and beyond. The luminosity of a quasar can exceed the combined light of the entire galaxy surrounding it by factors of hundreds or thousands. As the two supermassive black holes of Milkomeda approach their merger, the gas disturbed by their orbital dynamics may fuel a period of active accretion. This is speculative. The exact gas content of the merged galaxy at this stage and the exact dynamics of the final black hole and spiral are not known with the precision required to predict whether a quasar-level event will occur. But it is physically plausible, and the observation of AGN activity, active galactic nuclei, the less extreme version of the same process, in many merging galaxy systems, suggests that black hole feeding is common during mergers. If it happens, the galactic nucleus of Milkomeda will be the brightest object in the local group by an enormous margin, for a period of tens of millions of years. Then the merger completes, the two black holes become one, the accretion settles, the quasar, if it blazed, fades, the galactic nucleus quiets, and Milkomeda continues on its way. A single elliptical galaxy, in a local group that is slowly losing its membership to Milkomeda's gravity, as the smaller galaxies that once orbited the Milky Way and Andromeda are gradually absorbed. The Magellanic Clouds, those irregular dwarf galaxies visible from the southern hemisphere on your first night, satellite galaxies of the Milky Way, are long since absorbed. The Triangulum Galaxy, the third largest member of the local group, has its own complex trajectory, but models suggest it too will eventually merge with Milkomeda. The dozens of smaller dwarf galaxies will be consumed one by one over the billions of years following the main merger. Milkomeda grows by accretion, as it has always grown, as all large galaxies have grown, not in isolation, but by merging with smaller structures, incorporating their stars, adding their mass to the whole. The Milky Way itself was assembled by mergers. Its large stellar halo, the diffuse population of old stars surrounding the galactic disk, is the remnant of smaller galaxies that were absorbed in the early history of the Milky Way. The disk itself may have formed from gas that was disturbed and resettled by early merger events. Andromeda shows similar evidence of a merger-rich history. The stream of stars known as the Andromeda Stream, a vast arc of stars stretching hundreds of thousands of light years from Andromeda's disk, is the remnant of a smaller galaxy that Andromeda absorbed relatively recently in cosmic terms. Both galaxies are made of the remains of earlier collisions. Milky is the next chapter of the same story. The pace has slowed, the sentences have grown quieter. The scale of what has been described is enormous, not just the spatial scale of the collision, but the temporal scale. Billions of years have passed in this telling. The sun has ended, the spiral arms are gone, the two galactic centers have merged into one. The story is approaching its final phase. But it is not over. It will not be over for a very long time yet. In the quiet of the forming Milky, with the chaos of the merger subsiding and the new equilibrium beginning to establish itself, something is possible that was not possible during the first pass or the second, something that requires stillness to notice. The stars are still there. All of them, every star that was in the Milky Way on your first hillside night, every star that was in Andromeda, they are all still here in Milky, in new positions, in new orbits, changed by the passage of time and the gravitational disruption of the merger, but physically present, still fusing whatever fuel they have remaining. Nothing was destroyed. The merger was total, the identities dissolved, the structures transformed, and not a single star was lost. Not one marble hit another. The emptiness held. The enormous spaces between stars, those 4,000-kilometer gaps in marble scale, proved to be exactly the right amount of space for two galaxies to pass through each other, to reshape each other, to become something new, without touching the fundamental units of which they were made. This is the deepest truth of the collision. It was not destruction, it was reorganization. It was the universe taking two arrangements of matter and gravity and producing a third, different arrangement from the same components without losing anything. The atoms are the same, the stars are the same, the physics is the same. Only the pattern has changed. And the pattern will change again and again on timescales that extend far beyond the merger of Milky, far beyond the current age of the universe, far into futures that the human mind can describe mathematically but cannot intuitively hold. The pattern will keep changing. But that is the next part of the story. For now, Milky is settling. The sky is quieter. The old light shines. Your breathing has slowed to the rhythm of something much longer than a single life. The pace of the narration has matched it. Short sentences, longer pauses, the settling of something enormous into something stable. The merger is complete. Milky is here. And the universe continues, patient and immense and indifferent and extraordinary, in all directions at once. Sleep is close. Let it come. Not the Milky Way, not Andromeda, something that contains both and is neither. A new structure, settled into the quiet geometry of an elliptical galaxy, its stars distributed in a smooth three-dimensional swarm rather than the flat, organized disk you once belonged to. How long has it been since your first hillside night? The number is difficult to hold. 10 billion years, perhaps more. The universe itself is currently 13.8 billion years old. This moment is somewhere in the range of 23 to 25 billion years from the beginning of everything, in a universe that has been running long enough that its earliest chapters are almost incomprehensibly distant. The sky above you, above whatever ground exists within Milky, is different from any sky described so far. It is quieter. Not dark in the way your first hillside sky was dark, not luminous in the way the merger sky was luminous. Something in between, something that has no precise equivalent in tonight's experience. The stars of Milky are distributed in all directions. There is no Milky Way band anymore, no single plane of concentration, no pale stripe to orient by. Stars appear in every direction of the sky in a relatively uniform distribution, denser toward the galactic center, thinning toward the edges, but without the dramatic disk structure that once made the Milky Way so visually distinctive. The average color of the sky has shifted. Red, orange, the old light of aging stars. The blue-white massive stars that made the Milky Way's star-forming regions so bright, the OB associations, the young open clusters, the blazing supergiants, are gone. Not gone in the sense of destroyed, but gone in the sense of finished. They lived their short millions of years. They exploded as supernovae. They left behind their remnants, neutron stars, stellar mass black holes, and they are not being replaced. A gas that would have formed new massive stars was consumed during the collision-triggered star formation burst, depleted by the enormous appetite of the merger. Elliptical galaxies do not make new blue stars. What remains are the survivors, the medium-mass stars in the late stages of their main sequence lives, the lower-mass stars still burning steadily, and the vast quiet ocean of red dwarfs that will outlast every other stellar type by trillions of years. The sky of Milky is the color of embers. There is beauty in this, not the beauty of spectacle. The merger was spectacle. The tidal tails and the star-forming knots and the crossed galactic planes were spectacle. This is a different kind of beauty. The beauty of things that have lasted. The beauty of light that has been traveling for billions of years from stars that were already old before the collision began, arriving here in an elliptical galaxy that has absorbed 2 spirals and dozens of smaller structures and settled into something that will persist, more or less as it is, for billions of years more. Old light from old stars, still shining. Let us step outside Milky for a moment. Not far, just far enough to see its shape. From outside, Milky looks like what it is, an elliptical galaxy, roughly spheroidal, glowing with the warm orange-red light of its aging stellar population. No spiral arms, no disk, no prominent dust lanes threading through its structure. The dust that once filled the Milky Way's and Andromeda's star-forming regions has been processed, consumed by the burst of star formation during the merger, largely converted into stars, or dispersed into the hot halo gas. The surface brightness profile, the way the galaxy's brightness decreases with distance from the center, follows the smooth mathematical curve characteristic of ellipticals, bright in the center, fading exponentially outward, with no sharp features or structural boundaries. At the center, barely distinguishable from the surrounding stars by any means short of precise spectroscopy, is the merged supermassive black hole. More than 100 million solar masses, quiet now, no longer accreting at quasar rates, if it ever did, feeding only on the occasional star that wanders too close to its gravitational sphere of influence, producing a brief bright flare called a tidal disruption event, then quieting again for millions of years. The black hole is patient. Black holes are, in a sense, the most patient things in the universe. They do not decay on any timescale relevant to the current age of the cosmos. They accrete when material is available and wait when it is not, the Hawking radiation that will eventually cause them to evaporate, a process predicted by Stephen Hawking in 1974, operates on timescales so enormous that a black hole of 100 million solar masses will take approximately 10 to the power of 95 years to evaporate completely. To put that in perspective, the current age of the universe is approximately 10 to the power of 10 years. The black hole's evaporation timescale is longer than the current age of the universe by a factor of 10 to the power of 85. The black hole is not going anywhere. Step back inside Milky, return to the sky, the stars in all directions, orange and red, the warm ember-colored light of a galaxy past its peak of star formation, but nowhere near the end of its stellar population. Now look outward, past the edges of Milky, into the space that was once the local group. What do you see? Not much. This is one of the most striking changes in the sky of 20+ billion years from now. The universe beyond the local group has largely disappeared from view, not because it has ceased to exist. The galaxies are still out there, still populated with stars, still evolving, but because the expansion of the universe has carried them beyond the cosmological horizon. The cosmological horizon, the observable universe, is defined by the distance that light has been able to travel since the Big Bang. As the universe expands, this horizon grows, but the expansion of the universe is not simply growing the observable volume at a fixed rate. The expansion is accelerating, driven by dark energy, the name given to whatever is causing the accelerated expansion that was discovered in 1998 by observations of Type 1a supernovae, work that earned the 2011 Nobel Prize in Physics. Dark energy causes the universe to expand at an accelerating rate. This means that galaxies beyond a certain distance are receding from us faster than the speed of light, not because they are moving through space faster than light, which is forbidden by special relativity, but because the space between us and them is expanding faster than light can cross it. These galaxies cannot send us any signals. Their light cannot reach us. They are causally disconnected from us, not by any physical barrier, but by the geometry of an expanding universe. Tonight, on your first hillside night, the observable universe contains roughly 2 trillion galaxies. The cosmic web of filaments and voids that structures the distribution of those galaxies is visible, in principle, out to distances of tens of billions of light years. The cosmic microwave background, the afterglow of the Big Bang itself, the oldest light in the universe, is detectable from a distance of approximately 46 billion light years, the current comoving distance to the surface of last scattering. In 20+ billion years, almost all of that is gone. The galaxies that were visible tonight have been receding for an additional 20 billion years under the influence of accelerating expansion. One by one, they have crossed the cosmological horizon. Their light has been redshifted to wavelengths too long to detect. Their signals have become too faint to observe. They have not disappeared in a physical sense. They still exist, their stars still shine, their black holes still anchor their structures, but they have become causally disconnected from Milky. The observable universe of Milky's era is smaller than the observable universe of tonight. Much smaller. The galaxies that remain gravitationally bound to the local group, the ones that have not been carried away by the expansion, are the only galaxies Milky will ever interact with again, and the local group in the era of Milky has been steadily simplified. The smaller members have been absorbed. The major independent structures remaining are Milkomeda itself, and perhaps the Triangulum Galaxy and its remnant, in whatever state the merger dynamics of the local group have left it after billions of years of gravitational interaction. The universe outside the local group is, for all practical purposes, gone from view. The sky of Milkomeda faces outward into darkness. Not the darkness of your first hillside night, which was full of invisible galaxies, full of light too faint to see without instruments, full of the cosmic microwave background permeating every direction. The darkness of Milkomeda's era is more profound. The cosmic microwave background has been redshifted to microwave wavelengths so long they would require radio telescopes larger than Milkomeda itself to detect effectively. The background radiation of the Big Bang is no longer detectable. The distant galaxies are beyond the horizon. The intergalactic medium, the thin gas that fills the space between galaxies, is emptier and cooler and less luminous than it was. The universe is older, larger, darker. This is the fate of any sufficiently long-lived civilization in an accelerating universe: isolation, not by any catastrophe, not by any failure of technology or will, but by the simple, patient geometry of exponential expansion. The universe hides itself from anyone who waits long enough to see the hiding happen. Milkomeda does not know it is alone, of course. Galaxies do not know anything, but the fact of it, the extraordinary fact that the crowded, filamentary 2 trillion galaxy universe of tonight will have, in 20 billion years, reduced itself to an isolated island in an almost featureless dark, is one of the most consequential predictions of modern cosmology. The universe will forget its own history. Not metaphorically, literally. Any civilization that exists within Milkomeda in this era and attempts to reconstruct the history of the universe from observational evidence will find that the evidence is largely gone. The distant galaxies that would reveal the structure of the cosmic web are beyond the horizon. The cosmic microwave background that encodes the conditions of the early universe is undetectable. Even the expansion of the universe, which tonight we measure through the redshift of distant galaxies, would be difficult to detect from within an isolated local group because there are no sufficiently distant galaxies to measure. The universe in Milkomeda's era looks, from the inside, like a small, quiet island. Only the physics itself, the laws of nature, the composition of matter, the abundance of elements, would tell a careful observer that the universe had a beginning, and that beginning was enormous and hot and full of structure that has since expanded and cooled and spread beyond reach. Inside Milkomeda, the stars are still burning. The red dwarfs in particular, the most numerous type of star in any galaxy, the dimmest, the slowest burning, are still in the relatively early phases of their lives. A red dwarf with a mass of about 10% of the Sun's mass will live for approximately 10 trillion years. 10 trillion years. The current age of the universe is 13.8 billion years. A 10% solar mass red dwarf has barely begun. These stars faint, cool, burning hydrogen so slowly that their lifetimes extend into futures that dwarf the current age of the universe, are the lights that will remain burning in Milkomeda long after the sun's white dwarf has cooled to invisibility. They will be burning when the last supermassive stars have died. They will be burning when the last giant elliptical galaxies in the surviving universe have consumed their stellar populations. They will be burning faintly in a universe so dark and so empty that the concept of a night sky has become meaningless. Red dwarfs are the last campfires. They burn red and small, and for so long that the numbers required to describe their lifetimes require scientific notation to remain comprehensible. And they are everywhere. In Milky, they constitute the majority of the stellar population. They always did, in both progenitor galaxies, but they were invisible against the brilliance of more luminous stars. Now, with the bright stars gone, they are what remains. The sky is red-orange, patient, continuous. Your breathing has slowed to match it. There is something happening in the sky that requires a different quality of attention than the spectacular collision did. The collision demanded a wide focus. It was large and varied and fast-moving by galactic standards, full of new things happening in every direction. This sky asks for something narrower and deeper. The patience to look at a single old star and understand that it has been burning for billions of years and will burn for billions more, and that this continuity, the fact of ongoing nuclear fusion in a small, dense core, the fact of photons working their way outward through stellar plasma over thousands of years before escaping as light, the fact of warmth and light and chemical enrichment continuing without interruption across timescales that shatter any human concept of duration. This continuity is itself extraordinary. Not explosive extraordinary, not collision extraordinary. Quietly, persistently, unfathomably extraordinary. The red dwarfs of Milky are shining. They will keep shining. And in the dark between them, the remnants of the stars that have already ended their lives are cooling. White dwarfs, the crystallized cores of medium-mass stars like the Sun, are distributed throughout Milky in the billions. They are not shining by nuclear fusion anymore. They are shining only by the slow radiation of their stored heat, and they are cooling degree by degree over billions of years from the white-hot surfaces they had when they first formed, through yellow, through orange, through red, toward the dark. Eventually, on timescales of hundreds of billions to trillions of years, white dwarfs cool to the point where they no longer emit visible light. They become black dwarfs, cold, dark, dense spheres of degenerate carbon and oxygen, gravitationally bound to the galaxy but invisible, carrying the crystallized ash of nuclear reactions that ended long ago. The Sun's white dwarf is already cooling. Whatever temperature it has reached by this point in the story, it formed when the Sun died, perhaps 5 to 6 billion years ago in the story's timeline. It is cooler now than it was. It is moving along the cooling sequence, slowly, patiently, as physics requires. The atom that was in the Sun's core when it first ignited, the atom of hydrogen that began fusing into helium 4.6 billion years ago, before the Earth had fully formed, is now part of the white dwarf. Still there, still a specific atom in a specific location within a specific object. It has been through nuclear fusion, through the red giant expansion, through the planetary nebula phase, through the contraction to white dwarf. It is still there. The universe keeps its atoms. This is the right thought to end with. Not the scale of the collision, not the drama of the merger, not the isolation of the era, the keeping of atoms. The fact that the matter which makes up the sky you looked at on your first night, the stars of the Milky Way, the diffuse glow of Andromeda, the interstellar gas and dust, and the very planet you were lying on, is all still present in the universe of Milky's era, redistributed, reorganized, transformed through nuclear reactions and mass loss and chemical enrichment, but present. The universe does not lose its matter. It only changes the pattern. And the pattern has changed enormously from your first hillside night to this moment, from a spiral galaxy with clean arms and active star formation, a dark sky spangled with visible stars and a soft smudge above Mirak, all the way through 10 billion years of approach and collision and merger and settling, to this, an elliptical galaxy in an isolating universe full of old light and patient red dwarfs and cooling white dwarfs, and one very quiet supermassive black hole at the center of everything. Two galaxies became one, and the one is still here. Breathing slows. Sentences shorten. The sky is warm and red and very old. You have traveled across more time tonight than any human mind was designed to hold. You have watched the Milky Way absorb another galaxy and be absorbed in turn into something new. You have watched the sun live and die. You have watched the sky change from the familiar patterns of tonight into something unrecognizable, and then into something quieter still. And underneath all of it, underneath the tidal tails and the star-forming bursts and the black hole merger and the cooling universe, the same physics, the same gravity, the same nuclear forces, the same conservation laws that hold in the nucleus of every atom in your body right now, on this hillside, on this night. The universe is not different from what it is. It simply shows different faces of itself at different scales and different times. Tonight's face, a dark hillside, a faint smudge above Mirak, a confirmed trajectory, a future that will unfold exactly as the physics requires, on timescales too long for any human life to witness. Milky's face, old light, patient stars, a quiet center, an isolating universe that has moved most of its contents beyond reach. Both faces are the same universe. You are lying on that hillside still, in some sense, in the sense that you began there, that the story began there, that the smudge above Mirak is still there above you right now, tonight, in the actual sky above wherever you are, not billions of years from now. Now, the collision that this entire journey has been about is visible to you tonight as a faint oval of light in the constellation Andromeda. It is 2.537 million light years away. It is moving toward you at 110 kilometers per second. It has always been moving toward you. Everything you heard tonight is real. Andromeda is out there right now. If this story found you at the right moment, if it carried you somewhere further than you expected, or held you in a stillness you needed, a like and a subscribe to Quiet Science at Bedtime means more than you know. It is how this channel continues, how the next story gets made, how the science keeps reaching people who want to fall asleep to something true. Turn on notifications if you want to know when the next one arrives. And now, the sky above you is the sky it has always been. The same stars, the same patterns. Andromeda above Mirak, the Milky Way across the dark, the whole familiar vault of it, temporary and specific and yours, exactly as it is tonight, which is not how it was a million years ago, and not how it will be a million years from now. Just this, just now. The hillside beneath you, the cooling air, the stars in their places. Sleep well.